When you look up at the night sky, the stars and galaxies appear to sit in a perfectly balanced, harmonious system. But that geometric order is an illusion. If the universe had actually remained perfectly balanced at the moment of its birth, none of us would be here to see it. 13.8 billion years ago, the universe began as a singularity, an infinitely dense, hot point where matter and energy existed in a state of absolute symmetry. Physicist Max Planck defined the boundary of this earliest era. During the Planck Era, at the absolute beginning of time, the laws of physics were unified and balanced. Had this exact balance between matter and antimatter persisted, they would have annihilated each other instantly. The cosmos would have been erased, leaving behind nothing but a sterile, structureless void of radiation. Our existence relies on a sequence of specific departures from that initial order. In the first second of time, that symmetry broke in three specific ways that allowed matter to survive and organize. The first disruption occurred during inflation, a period of violent, exponential expansion that occurred less than a trillionth of a second after the start of time. Physicist Alan Guth provided the mechanism for this instantaneous stretching, which rapidly increased the size of the cosmos and forced its temperature to drop. This rapid cooling caused a phase change in the physics of the early universe. The single, unified force that governed the singularity began to split apart. That unified beam fractured into the four distinct fundamental forces we see today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. This initial fracture provided the dynamic rules necessary for matter to interact. Without separate forces pulling and pushing at different strengths, particles could never bind together to build complex structures. Next, as the universe continued to expand, the Higgs field emerged, an energy field that permeated space and began giving mass to the particles moving through it. Peter Higgs was the theorist who identified how particles transitioned from weightless specks of energy to objects with specific, measurable weights. This process resulted in a specific, unequal allocation of weight. The down quark was made slightly heavier than the up quark, which meant that every neutron in the universe became heavier than a proton. Because physics favors an energy slope from heavy to light, this mass difference caused neutrons to decay into protons. The universe was soon flooded with a massive surplus of protons. This arbitrary mass difference provided the hydrogen needed to fuel the first stars. Without this bias toward protons, the cosmos would have remained a dark collection of unreactive, inert helium. The most significant threat to the young universe was the presence of antimatter. Early energy transformations generated matter and antimatter in nearly equal amounts, which destroy each other on contact. Paul Dirac was the first to mathematically predict this mirrored existence, realizing that every particle of matter had an opposite, catastrophic counterpart. To prevent total cosmic annihilation, an unknown mechanism in the first second of the universe must have slightly favored normal matter over its twin. Experimentalist Chien-Shiung Wu proved that this preference existed. Her work showed that the laws of nature actually treat quarks and antiquarks differently, confirming that the symmetry of the early universe had been broken. The scale of our survival is incredibly small. For every 1 billion matter-antimatter pairs that annihilated each other, exactly one extra particle of normal matter survived. All the stars, planets, and biological life we see today are constructed from that microscopic, leftover fraction of matter. By the time the universe reached 380,000 years old, these imbalances were permanent features of reality. Temperatures cooled enough for electrons to bind to nuclei, forming the first stable atoms. This transformation cleared the dense plasma fog that had trapped light for millennia. Now, photons could travel across empty space, rendering the universe transparent. In 1964, astronomers used the Holmdel horn antenna to accidentally detect the stretched remnants of this ancient freed light. This faint, omnipresent glow is the cosmic microwave background. It is the visible evidence of the first light escaping the early universe's cooling plasma. The complex structure of our world, from the fusion in stars to the chemistry of our bodies, rests on these three specific departures from symmetry. Our existence is the direct result of these early cosmic imbalances.